Hi, and welcome to Material Physics 2. Now, you've seen a stress-strain graph before, but today we're really going to dig deep into every little bit of what's actually going on here and think about it carefully. And there's a few ideas that we haven't met here before. Some of this on the A level, some of it isn't, but it's all useful for the AS, and it's certainly useful for any of you going off to do any of your engineering. So, we've got a bunch of things laid out on this graph. There's one I haven't labelled, which is really cool. It turns out there's something called the true elastic limit. And that is when you get the very beginning of dislocation between crystals. So when you start to pull on anything, the crystals will just spend a moment and they'll sort of reorder itself. And that's technically elastic change, because when you let go, they won't go back quite to the same space. So this is called the true elastic limit. It's more of a theoretical thing than a real thing, because it's very difficult to measure and very, very subtle, but it exists, and that's cool. And it again gets you thinking about crystals and crystalline shapes moving within solids. So somewhere in this part of the graph, there's a new thing called a true elastic limit. Now we've got A, B, and C. One of these is the elastic limit, one's limit of proportionality, and one is the yield point. Pause the video, see if you can guess which order they come in. And the answer is, it's exactly the same order as my learning objectives. It isn't the same order as my learning objectives, so just keep you on your toes. A is the limit of proportionality. So this is the limit of proportionality, and that is defined as the point at which Hooke's law stops being true. So up until A, we would expect this line to be straight with a gradient equal to the elastic limit. So it's the limit of proportionality. B is the elastic limit, and that's actually after A. So between A and B, you'll notice the graph starts to turn, so it's no longer a straight line, it's no longer obeying Hooke's law. But crucially, if you took the pressure off at B, it would still go back to the same shape. So you get this little bit of room here where even though the stress-strain graph isn't a straight line, even though it's not obeying Hooke's law, even though it's not proportional, the change is still elastic, and if you let go, it will go back to the same place. So the limit of proportionality and the elastic limit are slightly different. Just after the elastic limit, you have the point which we call the yield point, and this is basically the point at which the material gives up, and you start to get massive deformation for only a small amount of extra load. Now, interestingly, it's different to the elastic limit because although there is plastic change between B or C, you start to see much more plastic change after C. Okay? Now, there's no real physicsy difference between an elastic limit and a yield point. They're both just measuring plastic change. Interestingly, within engineering, the yield point is often defined as being 0.2% deformation. So, if it had deformed by 0.2% of its length or more, then you've hit the yield point. Prior to that, all you've hit is the elastic limit, meaning that you can actually draw another line on this graph showing 0.2% deformation, and where that intersects with this line, that will be your yield point. So you can sort of do it that way, which is real neat. Okay, now normally, when we draw our graphs, we would just draw them like this, going off and then just breaking at some for each point. But interestingly, if you want to be neat, you can draw this line here where the stress suddenly goes up again because of something happening at D. We're not hugely increasing the load, but the stress is going up. Pause the video, think about the definition of stress, and see if you can work out what must be happening at D. The answer is something called necking, which is where, if you stretch something out enough, its cross-sectional area will actually start to shrink. And because stress is defined as force divided by cross-sectional area, if you shrink the wire, the stress will increase even for the same amount of force. And if you think about it, as we stretch a wire out and out and out, it would be unsurprising that at a certain point its cross-sectional area would start to shrink. So 1 and 2 show the same wire, they're breaking at the same point, but crucially, one of them we're taking necking into account. So now one we're showing that necking is happening, which is why the stress is going up, but number 2, we're assuming that it isn't. And so that's why you have 2 different ends to the same wire, depending on whether or not you acknowledge necking. So A is the limit of proportionality, B is the elastic limit, C is the yield point, D is where necking starts. Number 1 is the line with necking, number 2 is the line without necking. So that's everything on this graph. There's one last thing I want to leave you with, which is something called the theoretical yield strength. The theoretical yield strength assumes that if every atom in your metal was part of a crystalline structure, what would actually be the force required to rip apart those ionic bonds? Now, this turns out to be completely useless in practice because every metal is a polycrystal with lots and lots of individual crystals inside it, lots of spaces, yada yada, crystals moving past each other, but you can from first principles actually work it out as though you'd have to rip apart the ionic bonds. Never really happens, but interesting idea. Okay, this is a question of need for everyone. Enjoy your weekend. I'll see you next week.